For the last century, our understanding of gravity has rested on a single mathematical foundation: Einstein's field equations. They describe how mass curves space and how that curvature tells mass how to move. But in standard physics, these equations are an axiom. They are the unquestioned starting point of the theory, a rule we assume to be true rather than a consequence we've derived from something deeper. A long-standing objective in theoretical physics has been to move past this assumption. The goal is to build these exact equations from a more fundamental framework, proving they are a necessary result of the universe's basic mechanics. Without a derivation, the laws of gravity remain a given, with no explained origin. To fill this gap, a new mathematical foundation is required, one that doesn't start with space and time, but creates them. The observer-dependent theory of everything, or ODTOE, attempts this by starting with a network of observers. Its core premise is that the laws of physics emerge purely from the way these observers synchronize. When the first ODTOE paper was published, it included a specific disclaimer. The author admitted that while the framework could formalize causal layers, it had not yet achieved a full derivation of Einstein's equations. This left three specific mathematical requirements open to the field: deriving a tensor structure for space, identifying an energy source, and proving they naturally lock together into a field equation. The synthesis paper, titled XL, marks the completion of that challenge. It provides the mathematical chain that links these three requirements into a single derivation. At the center of this synthesis is theorem T0. This theorem mathematically constructs the gravitational field using only the primitives of the ODTOE framework. Under T0, the rules of gravity are no longer assumed. They are built, step by step, from the ground up. The proof begins by establishing a geometric framework without any pre-existing space. This is achieved through phi iteration. Independent points in a void attempt to synchronize, creating a relational web. The non-commutativity of these steps, the interference between different observer paths, generates curvature. Space-time begins to warp from these overlapping operations. By tracking this interference, the math successfully derives the geometric side of the Einstein equation, including the Riemann curvature tensor. Space-time is a structural byproduct of these synchronization attempts. It only takes the form of a pre-existing stage when viewed at a macroscopic scale. Geometry alone is only half the proof. The framework must also provide a source of energy and mass to fill that space. The ODTOE equations demonstrate that the collective coherence of localized observers is what we physically perceive as mass and energy. This leads to a calculation of the global coherence of the entire universe, which the theory uses to derive the cosmological constant. The result is a theoretical value for the cosmological constant of 0.688647. This matches the established Planck 2018 empirical data within a margin of 0.05 sigma. This calculation is a direct output of the mathematical framework, achieved without any artificial fitting or adjustments to the numbers. This theoretical result is anchored by the data collected by spaceborne observatories, which measure the large-scale properties of the universe. By matching the thermal footprint of the early universe, the framework connects its abstract synchronization math to observed physical reality. The final stage of the derivation requires the geometry and the energy source to lock together into a stable system. This occurs through phi self-consistency. It is a mathematical feedback loop. The curvature of space determines observer coherence, and that coherence, in turn, maintains the curvature. This continues until the system settles into a stable state. The proof demonstrates that this stabilized, self-consistent loop is the exact mathematical structure of the Einstein field equation. Theorem T0 provides the final synthesis for the 4-article ODTOE program. Because of this derivation, classical cosmic structures are now proven results of the framework's underlying mechanics. For instance, both Schwarzschild and rotating Kerr black holes are recovered as exact mathematical solutions within the ODTOE framework. The framework also predicts the complex orbital dynamics of our own solar system, specifically reproducing the perihelion shift of Mercury. The expanding FLRW universe model, once an ansatz, is now an exact construction derived from these primitives. Every verified phenomenon, from planetary orbits to the expansion of the cosmos, is shown to be a direct consequence of this derivation. Deriving gravity from observer synchronization provides a mechanical origin for laws that have been assumed to be fundamental for over a century. This framework establishes a new baseline for exploring quantum gravity, intersections with string theory, and the structural link between gravity and the observer. These equations describe a closed loop of observation, where the laws of physics are ultimately a reflection of the observer's own presence.